Hello everyone and welcome back to my channel. This is part 2 of the two-part series of the write-ups for UTCTF 2024. In this video, I will be going over the crypto challenges that I solved in the CTF. Remember to watch the part 1 video if you haven't already. Let's start. The next challenge I'm going to solve is in the cryptography category called RSA 256. The description is based on the military grade encryption offered by AES 256. RSA 256 will usher in a new era of cutting edge security, or at least better security than RSA 128. We are given with vals.txt values. So if I go on Ubuntu and this is the values.txt, we can see that n is quite short. So I can use this on factor db, paste it, factorize, and you can see both of our factors are right here. I open both of these and you can see both of these are p, which means prime. So we can just simply decrypt our RSA. So I'm going to open Python 3. You can see this is p and then this is q. Doesn't matter which one you choose. P times q is that, and then n is that, so I can check that it is true. Phi is p minus 1 times q minus 1, then d is power of e negative 1 phi. Oh, e is 65537, that's the most common one, and then this is our ciphertext, power of c comma d comma n, and then I can hex that. And most commonly what I do, if I see that it ends with 7d, which is a closing curly bracket, it's probably the flag and it decrypted correctly. I can do that and then just use bytes dot from hex, and as you can see we got our flag. Let's move on to the next challenge. The next challenge I'm going to solve in the cryptography category is beginner Anti-dcode.fr. I've heard that everyone just uses decode.fr to solve all of their crypto problems. Shameful, really. This is really just a basic Caesar cipher with a few extra random characters on either side of the flag. Decode can handle that, right? The opening curly bracket, closing curly bracket, and underscore characters aren't part of the Caesar cipher, just A to Z. As a reminder, all flags start with UT flag. And then we're given with our Caesar cipher.txt, which is right here. And so if I copy that, and as it says anti-dcode.fr, so we're not going to be using decode.fr, I'll use cyberchef. So I put my input and it's a Caesar cipher. Caesar cipher is the same thing as ROT. It's not necessarily ROT 13, but we can always do find UT flag, and we didn't get it, so I start from 0. UT flag, we didn't get it. 1, nope. 2, nope. 3, nope. 17, 18. Oh, and right here, where did it go? As you can see, we got our flag, UT flag, RIP decode. Let's move on to the next challenge. The next challenge I'm going to solve in the cryptography category is called bits and pieces. The description is I really like RSA, so I implemented it myself, a two-parter. So even though this challenge has 435 points and RSA 256 has 100 points, it has an unintended solution which is the same as RSA 256. Let me show you what I'm talking about. So if I go here, we're given with N1, E1, C1, N2, E2, C2, N3, E3, C3. So we can see that the E is same every single time, and the intended solution was that N2 and N3 share a common prime, so you can find their GCD and then you can decode these two, and then this one was factorable, I think, using Fermat's factorization. But in this case, all of them are available on FactorDB, just like RS8256. So if I put it here, I get my two prime numbers, P and P, that means prime. So I can copy this, go here, P1 and Q1. Okay, E is that, N1, C1. Now I can do the same thing. So phi is P1 minus 1 times Q1 minus 1. So basically the same thing as we did in RSA256. And then D is power of E comma negative 1 comma phi, and power of C comma D comma N and 1 and C1. Let me make this D1, and then hex 2 through all. So 2 through all is like remove the 0x and take everything else, otherwise bytes.from hex gives an error. So when I do that, oh no, it didn't work. You can see it's only a half or a third of the flag. So that means all three of these will decode to 3 parts of the flag. So I can add this to the flag. So flag plus equal to, okay, so that's our flag. Now I go here, so you can see we got our entire flag right here. So if I go here, bits and pieces, I can move this code, and you already solved this. Let's move on to the next challenge. The next challenge I'm going to solve in the cryptography category is numbers go brrr. The description is, I wrote an amazing encryption service. It is definitely flawless, so I'll encrypt the flag and give it to you. We begin with a download link and a connection. So I'm going to go over here, and this is the Python file. So thank you for using our encryption service. To get the encrypted flag, type 1. To encrypt a message, type 2. So if I press 1, it gives you the encrypted flag. I have modified the main.py myself to print the key, so this is helpful for us. Now if I run it again and I press 2, message, and then this is our key, and then this is the encrypted message. The actual netcat server doesn't print the key, but this is just for debugging purposes. You can see that the key changes. So if I run it again, message, then this is the key, and I get the flag and the key changes. So we have to see what's going on. So we have a seed which is 10 to the power 6, which is not a lot. Then it uses get random number, and get random number returns a seed and then modifies the seed. Then encryption, it gets its key from the get random number, and then this is the print statement that I put. It does a cipher, it encrypts it, and it gives the ciphertext.hex. So if we get the seed once, we can calculate the keys that are going to be next. So if I get my seed, I can calculate the next seed. So if I encrypt a message, I somehow get my key and decrypt it and see if it's correct, then I can use that seed to calculate the key myself and then decrypt the encrypted flag. So what I'm going to do right now, first I'm going to go to exploit.py. This is the basic importing and the get random number. So I'm going to run a for loop 10 to the power 6, and so what I'm going to do first, I'm going to go here, copy this much. First I do seed is I, so every time we change the seed, because the seed is modified here, so every time it will modify the seed, but our for loop it fixed the seed. Then this is the solve script that I actually used, so I'm going to use this to explain as well. So we're going to print I and equal \r will print it at the same place. Let me show you how it works. Python 3 exploit. So it prints it like that, and then this is our key using the seed. Then I can use the AES decrypt function that I put over here. Cipher is equal to this, and now note that our cipher text will change every time. And now let me tell you what this try except is doing. It tries to decrypt it. If it gives an error, then it continues. That means the seed is not correct, and this is basically it. And if it actually correct, so we can see if plain text is equal to message, I'll print found seed. Then now what happens, we found the key that was the seed and the key that was used to encrypt the message, but we need to find the key that is our encrypted flag. So to find the key which is used for our encrypted flag, we have to do this again and then get the key again. So I go here and in the if, then I print the key, I get the key, and after that I decrypt it again. So okay, and then right here this is what we need. So cipher, and I can just make this key, and then encrypted flag is this. We'll change this again and then we just decrypt it. So I'm going to go right here, numbers go brrr, and connect right here. Okay, connect to it. Let's see. So I do encrypt a message. My message is message, and then 1, and then it quits. So I copy this, go to my exploit.py, I make it right there. Then my encrypted flag is right here. Okay, so I can do Python 3 exploit.py. Oh, unexpected indent. Let's see, try. Oh, there we go. And as you can see, our script is running. It takes a little bit of time, but not that much. So like when that 1 becomes 99999, that means it finished. So it takes around a minute to run. Sometimes the seed is less, sometimes the seed is a big number and starting with 9. So yeah, as you can see right here, we got our flag. It kept on going because I didn't put a break or exit statement, but as you can see, we got our flag. Let's move on to the next challenge. The next challenge I'm going to solve in the cryptography category is numbers go brrr 2. Note that I won't show you how to solve this entirely because I use the same unintended solution as numbers go brrr. So let me show you. This is numbers go brrr 1. So you can see it takes our seed, the get random number function, the encrypt function, and in this we get our encrypted flag and we can encrypt a message. So remember, we brute force our key and check if that is the message that we sent it, and if it is, we then use this method to calculate the key ourselves and decrypt that use that to decrypt the encrypted flag. In this case, this is numbers go blur 2. In this, the same thing, get random number, encrypt, but here you can see it does not give us an encrypted flag. This time it asks for us to guess the key. So what we're going to do, we're going to do the same thing. We'll send our message, which was message itself, the string message, and we're going to brute force what the key is, and then we're going to use this to calculate our new key. We're going to do key.hex because that's what it checks, and once we do that, we're going to send the key to the server, and we just do that 3 times. See, you can see we need to give it in hex for the key. So once we calculate the key, we can do key is key.hex, and then we just send the key. So that's basically it. So I'm not going to show you how to actually solve this using a Python script. It's the same script as last time. Instead of decrypting it, we just send them the key, and it's 3 times. So yeah. Thanks for watching. Remember to share, like, and subscribe.